Hi everyone, I'm Greg, co-founder, CEO at Undo, and we're going to talk about time travel debugging. I'm going to show you what it is, and I'm going to talk about how we build it. Undo is not the only time travel debugging solution. There might be a little bit of Undo bias to it because, you know, that's what I know most about and care most about. Yeah, an interactive as possible session. Great, it's a nice small audience, so we can have lots of questions as they come up. Please don't feel you need to wait to the end. I definitely prefer kind of interactive style. And the more we go off script, the better. I think one of the most stressful talks, I give quite a lot of talks, one of the most stressful I've ever given, because this is the first one where my two children are in the audience, which is surprisingly intimidating. Yeah, let's go. Right, okay. So you might know this quote. It's quite a well-known quote. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? So it's by Brian Kernighan. He's kind of, you know, one of the real fathers of modern computer science. He invented C and Unix, among other things. And it's a good quote. And I think what Kernighan is getting at here is, like, keep it simple. Give yourself margin for error. You're not quite as smart as you think you are. But I think there's an interesting sort of corollary to this as well, which is that, and this is so overlooked in software development, that debuggability is like the limiting factor on how good the software can be. For whatever our metric for good is, how fast it runs, how small it is, how quickly I can write it, how extensible, whatever our metrics for good are, if we make it twice as debuggable, we can make the software twice as good. So it's this limiting factor I think is absolutely fundamental to programming, and no one seems to really give a shit. It's sort of this like washing up thing it's looked at, and I just think it's completely integral. I'll talk a little bit about AI later, of course, because this is a talk in 2025, so you have to, but also it's kind of relevant. And, you know, it baffles me that, well, I'll get into this, but like all this billions and billions of dollars of investment and excitement into AI writing the code, like typing in the code, is about 10 to 20% of a programmer's time, particularly on a large code base in a kind of enterprise setting, and more like up to 50% is spent either debugging it or understanding it. And so, you know, all this excitement over the small part of the job. Anyway, here to try and change that a few souls at a time. So without further ado, a little bit of audience participation. You have to answer exactly one of the following questions. So I'm going to say, raise your hands when I ask. And if you don't raise your hands to precisely one question, then you are just like a stick in the mud, no fun, kind of bad sport person. And you'll see why I'm asking this in a minute, because what I'm trying to do is get you in the habit of being off the fence. So it's going to be dogs or cats. So first of all, show of hands, please, for dogs. Ooh, and cats, got to be at least one. That is pretty much bang on 50-50, I think. It's in very interesting differences. I've never seen it be cat majority, I have to say. Dogs is the right answer, but well done for participating. Okay, so we're used to being off the fence now. So do we debug code by adding printfs or going into the debugger? Okay, adding printfs, you might remember this sort of quite well-known cartoon back in the day from XKCD. They're, you know, goofing off because they're compiling. What are they compiling? They've added a printf, almost certainly, right? 90+% of rebuilds that happen outside of CI are because someone has added a printf to debug it. I've made that stat up, but I stand by it. Versus in the debugger, you can see step, and it's gone too far. And so we can get into precisely one. Show of hands, and everyone's, oh, it depends. No, depends, right? You have to give exactly one answer. So is it printf?
That's my answer.
I don't want, you've got off the fence, right? Print. Okay. Yeah, we can maybe rechange. Yeah, but we have to. And then debugger. So bang on, 50-50. Right, okay, good. I always think it probably, the fact that I'm asking the question probably skews it a little bit debugger. So in fact, I think we're probably like 75, 2/3 printf in reality. Yeah, I think the reason why actually the answer is always it depends is because both answers are not very good. Unlike cats and dogs, there is no good answer here. The only winning move is not to play. No, so you've got, yeah, the problem, I'll get back to this, right, but neither of these are particularly good solutions, unless we give our debugger a little bit more capability. Okay, so I'm gonna run through is going to be a bunch of, sort of details on how this works and demos and stuff. But before we get into that, it's QR code time again. So the good news is you'll all have the QR code app like ready on your phone because you just used it. And you can win a year of a free Undo license, which is worth, actually, no, it's not worth it. It's worth a lot more than 7,900. It costs 7,900. Yeah. Sorry? Yeah. First bag is always free. Absolutely. Yeah. Right. Yeah, exactly. So this is a floating license, so you can share it among your colleagues, and then at work. Yeah. No, it's for real. It's a real. It's a yeah. No, there is value behind this. We don't expect to get your email addresses for nothing. Cool. All right, yeah, and given, sometimes I do this as a raffle. Sometimes there's like 100 plus, maybe even a couple of hundred people in the raffle. Your odds are good. These are some of the people who are using the technology, so you can see it's the point of showing this slide is partly because it's a bit of what Sam would call a flex, because I'm very proud of the customers that we have, but also the point is that this is real. What I'm about to show you is not just works on toy code, little kind of hello world type programs. This works on really big, millions of lines of code, complex, at scale enterprise software. That's a bit marketing-y, so on. So yeah, so let's think about this thing of debugging that I've claimed like dominates software development. What is it? What do we mean by it? And really, it's a process of thinking, how did that happen? Right? It's a kind of past tense way of thing that we're thinking about. So I don't mean like how did that happen or how did that happen. What I mean is we have an expectation of what our program is going to do, and reality diverges from that expectation at some point. And the process of debugging really, we call it debugging, nearly all of it is not taking the bugs out as much as finding where the bugs are, right? It's more about bug discovery. And what we're looking for is this point where reality diverges from our expectations. Okay, might look more like that, but this is a hard thing to do. So the program's doing billions of things every second, and it's every time what we don't do is run it a whole bunch of times, and each time we're getting like a piece of the jigsaw puzzle. Okay, or maybe you can think of it as like some kind of Sherlock Holmes thing. We're getting clues. We're getting clues as to what's gone on, and we're trying to kind of deduce the reality. Tends to feel more like that than Sherlock Holmes at times, but that's what we're trying to do. So what makes bugs hard to find? I think there's two axes to this, right? Two things that define how hard it is, because obviously there's a huge variation in this. We've all been there. Lots of bugs, they're obvious. Almost straight away, you know the root cause when you see the crash, and there are others that can take literally years, right? And I think there are two things that define this. One is, sorry if you're at the back, you might not be able to see, but one is the time, how long is it between the bug itself and observing the failure, the crash? If if the bug is you didn't check for null when you should have, and you dereference it at that point, it's right there. You can kind of see it pretty easily most of the time. If the bug is some piece of state gets corrupted and I don't trip over it until a long time in the future, much harder. And this is why assertions are so valuable, right? Because what they do is shrink that time. And the other metric is how deterministic is it? Does it fail in the same way every time? Or does it fail differently every time? Or maybe it fails only one run in 1,000 or 1,000,000. And if we're kind of in the top right-hand corner, that's where it gets really interesting. If they're non-deterministic, it's like with that puzzle analogy, it's like I'm doing a jigsaw puzzle and every single piece of the puzzle is for a different picture. And when we're up in the top right-hand corner, that's where it gets really fun. And particularly if we're up here with so-called Heisenbugs, where we try and do something to get a clue, we add print statement or we attach debugger or something, and the bug goes away or changes materially. And these are just like super hard, right? And this is where I think time travel really comes, the further you are here, the time travel comes in, and we'll get into kind of why, I think just about right now. So that's enough slides for now. Let's see what this looks like. So I've talked about it in a very abstract concept, and it's much easier just to see it, or just show it, than to explain it. And the best way to show anything is by running Doom. But I'm running Doom, you'll notice, prefixed with this live record utility here. So, oh, why is that? No sound. That's really annoying. There's no sound. It's much better with sound. Oh, there is sound. There's sound, but it's coming out of here really quietly. We'll have to remember what it sounds like. Okay. It's much better with sound, this demo. I could do the sound effects, but I don't think that will really work. I practiced this earlier. Sam laughed at me for how bad a gamer I am. All right, that'll do. It's not really to show you how to play Doom. The point is, I'm going to navigate a code base that I am pretty much completely unfamiliar with, and I'm going to find out important things about what happened in that non-trivial, real, small piece of, code, but it's a real piece of code. So let's load this up into VS Code. I always think it's so cocksure of Microsoft to make VS Code called code. Anyway, so here's the code, and what I'm going to do is load up. So I took, actually, before I get to that, let me show you. So I took a recording by running this with live record. So that's the recording I've just taken. That's the one I did before when I was practicing. So you can see, okay, it's 400 odd megabytes. It's not tiny, but it's not like ridiculously large. And I'm going to load that up. This recording contains everything that the program did. It's sort of like having a core file, if you're familiar with those, but the core file just has the full program state at one point in time, typically when the program crashed. This is almost like having a core file for every single instruction that executed, complete program state for everything. And yeah, I know one thing about this program, which is that there's a thing called iVideo buffer, which is 320 by 200. Can you see that down at the bottom? Probably, no, yeah. Anyway, let me resize this window because I think we can probably do that. I'm just trying, it's quite small text as well, isn't it? But I think that's going to work better. Let me just expand it out. So, yeah, there's a 2D array called iVideo buffer, which is 300. Oh, for God's sake! Which is 300 by 200. So I can show that as a frame, so we can see. Zoom in a bit there. So this was at the point that I terminated the game, right? So this is I've got them at the end of time. And what I want to do is use the recording to navigate back through the program execution to find like the line of code where I killed one of the zombies, okay? So if I just hover my mouse over a bit of blood there, that's probably going to work. So I can look at the, you can see down here, that is 172.115. That's the coordinates at 172.115. Did I say? I've already forgotten. 172.115. 172.115. So got this thing called my video buffer. Each row is 320 pixels. So that's that pixel. It's value 47, which is kind of RGB red. So how can I find out when that zombie got killed? Well, what I'm going to do is follow both the data and the code flow through so I can see what happened. So I'm going to go to the line of code where that element of the array most recently changed. The easiest way to do that is with the last command. And because I've just looked at it, I can go last $1. So this is going to go to when the line of code where that most recently changed. You can see here, I'll scroll down a little bit. Hang on a minute. Get my window furniture right. So I've got this little timeline. So I'm right at the end of time here. I can also see it tells me I'm at the end here. So let's see when that changed. Okay, so we've gone back, not very far. We've gone, but we're 99% of the way through. the gameplay now. And the thing has been updated. I've got a call stack here, and I can see, yeah, okay, I'm draw column. Okay, so yeah, I'm in some kind of paint to screen routine, which makes sense. I've just updated the pixel. And I can see on my call stack, there's a thing called draw sprite. I'm trying to find out when these things died. Remember, that's a bit of blood from the sprite. So yeah, what I'm going to do is uncall, going to go up the call stack here. This is a little bit like popping up the call stack, but I'm actually rewinding in time. Everything is, it's not a guess, all the global state and everything is going back to what it was. And I'm going to go to this draw sprite, and we can take a look at the sprite. So there's a thing called sprite. It has, don't know what these x1, x2 coordinates are. They sound like they might be kind of relevant. So when it's last moved, that's probably getting to the point where I've killed it. So I'm just going to do last again. So we're just pulling that thread of data as we go back through the program execution. Okay, we're now at 93%. And I'm in something called project sprite. Project sprite. Okay, that's when this X1 was last updated. There's a thing. Let's see what thing is. Okay, thing has lots of stuff. This is like the original AI here, by the way. We looked into, well, one of my colleagues, Mark, started poking around on how the AI works in Doom. It was depressingly simple, but I guess that's not surprising. What else have we got? Well, we've got a thing called health, right? So thing has a property called health, -5. That sounds kind of dead to me. So if I go last thing health, this should go back to when the health was something different from -5. So we go back. Okay, we're now 87% of the way through, and was -5, now 10. So I've gone back to when it would seem to be pretty alive. Let's have a look at the video frame here. See if this is right. And yeah, probably that's like just before. But the only thing is, I'm inside the game, but the video buffer hasn't been updated yet. So I'm like one frame behind kind of the action point. So let's think. Now, I remember before I was in a place which was updating the screen, but I can't remember what that was called. That's okay. Let's just set a bookmark. I'll call it die. Because I want to come back to this point. And then I'm going to go back. This is the undo button here, which is a little bit like the back button in your browser. I'm going to go back to the previous things that I was looking at to get back into this thing where the pixel was updated. And yeah, back to Future Indeed. And like, I think I was here, and I've just moved these. Let me just move these.
So you're now going forward.
Well, yeah, I'm going forward, but technically I'm going to where I most recently was. Which might take me back in time or might take me forward in time, depending on whether I most recently did a forwards or backwards operation. I can't drag this damn window furniture. Hang on, I think it's because I've messed my... So this is... Okay, yeah, I can do it. So yeah, so this is what I was looking for, D-display. I was trying to remember that was called, D-display. So that's, I guess, like draw display or something, or update display. So if I go, you go bookmark back to that previous bookmark. So now I'm back to where I actually shot, where it actually dies. Now I can put a breakpoint on D display, and now I'm going to run forwards to that breakpoint, and that's at the beginning of updating the display. So if I run out, that'll run through the whole display function to the end, and that should update the display, I think. So now, if we show the frame, look at that. Whoa, yes. That is definitely a dying zombie. So yeah, how cool is that, right? I've managed to navigate through. I mean, obviously I have done this before a couple of times, but genuinely, you're able to navigate through a non-trivial code base with no real knowledge of what you're looking at, and just by following the code flow and the data flow through, we can find out what we want to find out. And sometimes we even get to play Doom. Cool. All right. So that was fun. I want to get into now the details, like how this works, how we built this. But before I do that, let me hold my own beer. Any questions?
So you have like a bunch of additional navigation things that send you through different stages of your reverse debugger. So you explained a few of them, but it's quite a big part. Is there anything else that's sort of
Okay, yeah, I think you've probably seen most of the key features, but I always type, so I can't really remember what the icons are, but let's have a go. I reckon that is create a bookmark, and that's go to a bookmark. So we saw me doing that from the command line. That is something else, don't know what that is. That is the last command, go back to when something changed. Let's go back to the beginning. That's reverse out, so go to the caller of the current function. That's reverse step into, so I'm going to go back one line, but into the function that's just returned. We didn't do that. Oh, I didn't do this. This is good. I should do this. This is just like a reverse next, right? So this is actually makes it quite a little bit easier to see what the heck is going on sometimes. So if I click that, it's just literally going back, just unwinding back over the time, and I can go forward. And of course, as I do, critical to note that like all my locals aren't here, but all my data and everything is changing as I go back and forth through time. It's not just the code execution. Reverse continue, so just run back until the most recent interesting thing happened, breakpoint, whatever. Go back to the beginning. Undo, we saw that, redo, go back, go, and then these are just basically the opposites, go forward, step forward, normal kind of debugger commands. Start again, exit the session. Something Copilot, I guess, but that's probably not us. Yeah.
Can I ask a question?
Yeah.
What does it do with multi-threaded apps?
Yes, I've got a slide on that, which I'm going to get to. And then this is a multi-threaded app, though, before I get to that. So we have so here are all the threads. Okay, 6 threads, not a huge number, but there are lots of threads. And we go back and forth through these threads kind of in lockstep. So all the threads move together, forwards or backwards, or jump around to where we were. I'll get into the sort of details of how we implement it in a moment. Yeah.
When you were doing the recording, it was pretty much real time.
Yeah.
But it is a 30-odd-year-old game designed for the hardware at that time.
Yeah.
Was it like on today's hardware, something a little bit more dynamic?
Yeah. So it depends, but you will see it's quite common to see, in the good case, like half speed while recording. So it is a real overhead. You wouldn't just record this like all the time just in case, but half speed is perfectly achievable. It's not uncommon to see 5x, 10x slowdown, especially with very multi-threaded programs. We'll get into that in a bit. So yeah, it's kind of what performance characteristics are, not such that you would turn it on all the time, but good enough that you can turn it on in pretty demanding applications to try and catch particularly those intermittent nasty things. You can kind of turn it on and leave it on, certainly in like with tests, with intermittent flaky failing tests. Yeah, absolutely, yeah. So that's another way. So I would say the performance characteristics are more like the sanitizers than say Valgrind. That sort of range. Similar with memory as well. So the general rule of thumb is you need twice as much time and twice as much memory to run this than you would normally need. Again, mileage will vary, but that's kind of roughly what we're talking. And yeah, I'll get into the implementation a little bit, and we can see kind of how that's possible. Because yeah, most people's assumption when they see this is like, hang on, that's a core file for every single instruction that ran. Or maybe we could do it just with like a delta, but even then, that's a lot to store and a lot to get in. So yeah, we'll get into that. Is there a question here? Yeah.
How will programs allow like recepting bits or recepting like Ethernet packets?
Yeah, beautifully. Yes, but that's a key. This is the key right thing, right? Well, all these questions are key, but like, yeah, what do you do? I mean, when I record and it like removes a file, and then I go back and that file doesn't exist anymore. So how am I like reading from it and things like that? So what we're doing is capturing all of those inputs, and I'll get into the kind of details of that. But I think now's a good time to get into the how, because that's definitely where we're going with the questions. So one thing, so this is all kind of time travel sci-fi things we could pick. I like this one partly because I think it's kind of cool, but also because unlike this is kind of the original time travel story. This is H.G. Wells' time machine. Yeah, sorry. Yeah, H.G. Wells' time machine. Sorry, should have said. And unlike nearly all of the other time travel stories, he doesn't really change history. He's an observer, and that's what we're talking about here. We're going back. So that's often, that is one common question. Can you go back and change things and see what would have happened? No, it's not that, well, you get into paradoxes, okay, if we do that. So generally, yeah, so it is just, this is about observing. But when it comes to this, what this is for, that's all you really need, is to know what happened. So let's come back to printf versus debugger and why I think this is important. So printf debugging, or console log, or whatever language you're using, it's about, I said before, it's about seeing what happened, past tense, and that's what printf does. It gives me a story of my program's execution when I print out that log, okay? Whereas debuggers, if they don't have time travel, they just let me see what's happening right now. I mean, okay, maybe I get a backtrace, and that's kind of a bit of history, but generally not really. On the flip side, with the debugger, I can ask any question of my program that I want. I don't have to recompile it, rerun it. It's just there, and I can query to my heart's content. And with print style debugging, I've got to change my program and run it again in order to find out that information. So that's why time travel, I think, is so important, because we can do both. We can see what happened, and we don't have to change the program. And particularly with those kind of non-deterministic, kind of flaky issues, that's really, really helpful. Yeah, so let's think about how do we build this? Because I think it's kind of an interesting computer science kind of challenge. And there's a number of design decisions that we have to take here. And I'm going to introduce a number of other implementations. They're not the competition, because there isn't really any competition, but alternatives, we'll call it. And yeah, so how can I remember what happened? So I've used this phrase a lot, what happened. That's what debugging is all about, and that's what time travel is about. You go back and you can see what happened. Well, a more kind of computer science way of asking the question is, what was the previous state? Okay, and there's two options to this, really. I can save the state as I run, or I can recompute it. Those are my two options. And recomputing it sounds very attractive, because saving it is going to be very expensive, right? If I'm saving it, even if all I'm doing is saving what changed, every single instruction that ran, something changed, otherwise I'm live locked, right? So that's at least some state, probably 8 bytes at least, probably 16 bytes, every single instruction, billions of those every second. It's a lot to save. Recomputing sounds good. If I've got some statements, they're naturally reversible. So if I've got a equals a plus 1, and I know what a is, and I've just executed that statement, then reversing it is trivial. But if I've got a equals b, a becomes b, I can't reverse that statement. If I've just assigned b to a, or a to b rather, then I don't know what was in a before that statement ran. There's no way to get that back if I haven't saved it. Actually, even a equals a plus 1 is not really reversible, because it's probably affected the flags. And even I don't know what the previous instruction was, because maybe I jumped here and the previous instruction wasn't the one just behind me. So saving it's not practical, recomputing it doesn't work. Unless what we do is re-execute, okay? So the kind of fundamental kind of observation here is that computers are basically a great big deterministic function. If my f of x, and if x contains the entire state of my program, then I do one instruction on the CPU and it will just compute the next value, okay? So that itself is not reversible. There is a thing, by the way, reversible logic. It's really interesting, I think, because it turns out that there's an E equals MC squared type equivalence for information. If you destroy and create information, that consumes a certain amount of energy. And so there's this thing about reversible logic. If you make our logic genuinely reversible, it consumes less energy, because we're not destroying information as it runs. Really kind of cool, but total mad, university stuff. You can't buy this hardware, and no one's really seriously talking about making it. So they're repeatable, they're not reversible. So what I can do if I want to go, say I've run my program 1,000 instructions, and I want to go back one, I can go to the beginning and play forwards 999, and that's logically equivalent to going back one. That's in fact what we do all the time. So we just have some snapshots, and when I go back in the demo, it's not really going backwards. Okay, now in fact we can see these. Oh, that's wrong. Yeah. Okay, so here's my snapshots, got 30 odd. And when I go back in time, that's where we currently are, it will go back to the preceding one and play that forward to just before where we were, giving us the illusion of going backwards. Catch is, computers are completely deterministic except when they're not. So we have to deal with these non-deterministic inputs, and that was to the question before, how do you deal with interrupts and signals? But what we do is to save those when they happen at record time. Just those non-deterministic things, right? So, accesses to the file system, network, user input, time, all that stuff. You capture that in an event log, which I can also see. I'm not going to go the whole thing because it takes like forever. But if we go like that, that'll probably give me a bunch of events. And then we can see these are all the non-deterministic events. But they are a tiny minority. Like 99.99% of what the program is doing is more like adding two numbers together, moving a number from here to there in memory. And so with that, I can now get something that performs reasonably and works at scale. So we've got snapshots and we've got event log, and that's kind of this approach with deterministic re-execution that we do. Not every solution does this. In particular, the Microsoft, there's a thing from Microsoft called TTD, Time Travel Debugger. Microsoft seems to like to TLA everything. It doesn't. And I met the people from Microsoft who built this in the end. And we talked about why they don't do the re-execution. And the problem is that, so in Linux, there's like about 500-ish system calls, depending on exactly how you count. In Windows, there are thousands and thousands, and no one knows what they all do. Even Microsoft don't know, right? Oh, and they can change. There's not even a stable Windows ABI. So they just couldn't do it that way. They have to sort of save everything as it's running, and as a result, it generates way more data and runs quite significantly slower, but it does at least work. And if you're on Windows, you've got that option. Non-determinism. So if we think about this into a Linux or Unix or any Unix-derived system, what are the sources of non-determinism?
System calls.
System calls, excellent. Yes, so any system call is unpredictable, right? Given the state of the program, I don't know what the system call is. If I did know, then it shouldn't be a system call, it should be a library. So system calls, yes, I think. That's my first one. Good, you're even in order. Right, there are 5 in total. I'll give you a bit of a clue. What are the others?
User input.
User input, but that would be a system call, wouldn't it? Right, so this says, yeah. So we put that in the system call bucket. Signals, yes, that's another one. Yeah.
Shared memory.
Shared memory. Have you seen this talk before? Very good.
Mobiles and
You have. Right. Very interesting. 2 more?
timestamp counter.
Yes, so reading the timestamp counter. So that was that there's certain instructions are not predictable. So if there's an instruction to read the timestamp counter, that will give a different result every time you do it. On modern hardware, there's even like get me a random number instructions, and so these are. You could argue that system call is an instruction and a system call is an example of a non-deterministic instruction, but I kind of think of them separately. One more. It was asked. Someone asked a question on it. Threads. Thread switches, thread interactions. So, yeah. But that's it. If I capture all of those, that's complete. There's nothing a Linux program will do that is not one of these things. Shared memory, by the way, I define that as so most memory, when I read from it, I read what I most recently wrote. That's kind of the point of memory. But sometimes if it's shared with another process or with a device or a kernel or something, when I read back, I'll read something different than I last wrote, so that's shared. So we need to deal with that. But yeah, that's it. That's the complete set. It's kind of someone asked on one of these talks, how do we know? And the answer is you can't really know, but we just kind of figured it probably was, and we'd find out soon enough if it wasn't. And so far, it looks like that is complete set. So we can re-execute, we can try and store things and go backwards. If you can possibly re-execute, that's definitely, I think, the best approach. Like I say, if you can, it's hard. That's the only thing. Really hard to do. It's kind of irony that this is some of the hardest stuff to debug, because if you just slightly don't get everything, you're sniggering, you've been there. If you slightly don't capture everything, you always, that thing of the top right-hand corner of the hard ones, all the bugs are up there in the top right-hand corner. It's horrible. We did get to a kind of singularity moment, if you like, where we could, the tool became complete enough to debug itself, and then things got way easier. But it was quite a long time until we could do that, because it does lots of shared memory and threads and asynchronous execution and stuff. So it took us quite a long time to get there. But once we did, yeah, life got a lot better. Second design decision here is, what's our boundary of what are we going to record? And if this is a C or C++ program or Rust program or some kind of compiled native program, then it's probably like the program boundary makes sense. But if it's like a Java program, maybe I want to record not the process, because the process is the JVM that's running the Java program on top. Maybe I want to record just the Java program. Or maybe I could record just a single thread or just a single function, or I want to do the virtual machine. Process is kind of the winner, actually, surprisingly, almost always. So yeah, we started off with C and C++. We then made a Java version of it, and that was a big design decision. Do we record the process, including the JVM, or just the Java code? And we decided to do the whole process, mainly because that's what we already knew how to do. We already had most of the tech to do it, and also things like JNI functions and stuff. But yeah, I'll get into some of the other. It's a nice thing with the process is it's really well defined, at least on Linux, right? So we've got those 5 sources of non-determinism. We know what memory, apart from shared memory, we know very clearly what memory is inside the process and what's out. With things like a thread, what's the boundary of that thread, right? Is it just its stack? What about sharing other global data with other things? It becomes really difficult to kind of define. And even a Java program, like even the JVM, although it's kind of simple and well defined, it is not as precisely defined as a process, which tends to be sort of defined by the CPU. Virtual machine also works. There's some time travel reversible technologies on virtual machines. VMware had one back in the day. They gave up on it, sadly. You can do it with QEMU, however you want to pronounce that these days. That also works. But at the process, what I mean by the process level, so if I've got these processes running on the kernel, this is my boundary. So everything is in here, right? libc, everything that's not in the kernel is actually inside my process, and that's what I'm recording, which is also useful because it's quite easy to scribble over your memory through libc, right? If I do a strict copy with bad arguments, the kind of corruption happens inside libc. I want to know that. Sometimes libraries have bugs. Or another process. It's the process boundary. And then the next one is, how are we going to track time? Sounds, well, either very simple or very kind of exotic. I don't mean in this kind of weird, time travel, paradoxes, paths of time. I just mean really simply, what's the notion of time? If I'm stepping back, imagine I'm in a loop. My loop's done 100 iterations, and I'm stepping back through the loop. I want to stop in that. I want to be in that 100th iteration until I step to the top of the loop and go around again, right? So I need to know precisely where I am. Also, if I'm replaying a signal, asynchronous signal, that needs to happen exactly the moment that the original one came. So we need a very, very precise way of tracking time. And that turns out to be quite hard to do efficiently. There's really 2 ways that you can do it. JIT, which is JIT or not to JIT. So we can JIT, and that's actually what undo does. So we do a binary translation as the code is running. We get equivalent binary to the original, except there's enough hooks in it for us to count where we are. Basically, we count backwards taken branches, and that's enough. Or you could use the performance counters. Performance counters give you a kind of instruction level thing of where you are, although none of the CPU manufacturers actually guarantee that they work. On modern CPUs, in some circumstances, they do work nicely. The nice thing is it's nice and simple. You can just run your native, instrumenting the code is painful, and it can be very fast, but they're very pernickety on where they run. So if you're trying to run, the public cloud people, for example, won't pass through the performance counters because of concerns about side channel timing attacks and all the rest of it. Or not all CPUs support them precisely enough to do that. But it's good where it works. But JIT gives you much more flexibility. It also lets you do things like tracking shared memory, which I'll get to if we get time. So that's what we do. RR, if you're familiar with R, anyone used RR? Jack has. Oh, damn it, I forgot to ask something, right? So before you saw about this talk and you came here and stuff, who'd heard of time travel debugging like as a concept? Who'd tried it? So Jack, I know because you're an early customer and you built one and no one else has tried it. And this is, I find, like excruciating, really. I think it's so powerful. Hopefully you could see that from the demo. It's available these days. If you're on, I'll get into some of the different implementations. Like you don't have to come to Undo and pay us lots of money, though you can if you want. But there are other options. And like everyone should at least try it. I find
The problem that it's not that well done.
it's just not, yeah. Well, but it's, you see, usually when I ask this, I see, we cancel here, about half the hands go, and last time I did this talk was in London, and it was, Herb Sutter was up next, so everyone was there not to see me, and there were like 200 people, and I asked the same question, and I said like half the hands go up, yes, I've heard of it, which is frustrating, why haven't everybody heard of it, but half the people have, 2 or 3 have actually tried it, right? So it's not just an awareness challenge. Doesn't have those. There are open source versions of it that you can use. So, that I would think at least try, right? So I urge everybody to, you can go and like, if you're not lucky enough to win the raffle, you can go and download a free trial of Undo, or you can just go and use RR if you're on Linux, or if you're on Windows, you can go and use. The only one that isn't a solution actually is on Mac. There is no solution that I know of on Mac, but everything else, they kind of, there are, and I get into it. So we're going to rely on memory-only determinism. This is kind of the...
That's a question about the time thing.
Yes.
So with a binary different time quantification,
Yeah.
and you have an inverted logical clock that you're doing, and so that's the clock that you're using for all the events.
Yeah.
So do you like something to make sure that there's a sequencing between things on the different threads?
Yes. Yeah. So I've got a slide on that. So yeah, actually, let me get to that because that's here. So we kind of cheat, and most of the tools do this. The only one that doesn't, actually, interestingly, is the Microsoft one and the hardware-based ones. We cheat, and we serialize those threads down. So in fact, in reality, only one of them is running user space code at a time. So this does give you, worse slowdown than if you're running only a few threads. Not as bad, not nearly as bad as people think it's going to be when you say that this is what we do. Because most people go, well, I've got 16 threads on my 16-core machine, so therefore I'm going to... there's 2 things here. One thing. You don't get as much parallelism as you think you do. Like, your program probably isn't as parallel as you think it is because you've got locks and things like that. And the CPUs aren't. Like, the CPU will run faster if one core is active than if lots of cores are. And you can do all of your OS level stuff genuinely in parallel. All your I/O and system calls and things happen genuinely in parallel. So I'm not saying that there's no penalty to do this. Of course there is. And the more threads you have, the worse your slowdown will be. But it's not as bad as you would think. And the other thing people often think is, well, then I'm not going to be able to debug race conditions, right? Because if I'm like predictably serializing the threads, all my race conditions are going to go away. That's not true. What we do is, and what most of the things that use this technique do is to preemptively schedule the threads. So race conditions are still totally possible. In the old days when we had single core machines, if you have multi-threaded programs, you still got race conditions, right? There is a certain class of race condition that at least today, we do actually know how to solve this, but we haven't done it yet. At least today will not reproduce. So if you have a missing memory barrier and you get the kind of out of order weirdness on modern multiprocessor shared cache architectures, then those race conditions just go away when you're recording. But they're unless you're writing library locking primitives, they're very rare. Like most people don't even get to see them. And all the other races totally will reproduce. In fact, we have a thing we call thread fuzzing, which will deliberately perturb the thread scheduling to make race conditions more likely to occur. So a lot of races, it turns out, we've got some really nice benchmarks of this that show a very simple program that will fail with a race condition that will fail running normally after about an hour. And with thread fuzzing, with our latest and greatest feedback-directed thread fuzzing, in less than a second with recording. So it can, and the point is, once you've captured that race condition in a recording, it's really, really useful. So race conditions is one of the killer features for this technology. What's going on there? That's a weird, messed up slide. So yeah, I've got a sample of some of the different implementations of this. So undo obviously is the best. RR is, it's there, it's free. It's very good. I say in general, if RR works on your program, you should use it. And where it works very well. It's just a little bit limited on the kind of systems it can work on. It can't work in multi-tenant cloud, can't work with shared memory, can't work on ARM unless you have certain, there's a whole bunch of limitations, but if you don't fall foul of any of those limitations, just use RR. WinDBG, and that's where Microsoft's TTD is involved. Replay.io, which I mentioned to you earlier, that's the web-based thing. And then ODB is the omniscient debugger, and this is the Java thing, which is actually really old, but that was the first thing I saw that did this. And when I saw that, someone showed me a video of it in Java, and I was just like, immediately, that's amazing. It's a shame we can't do it on C and C++ code, because that's where I live. And then that was in my mind for several years until we figured out a way to do it. And then if we look at these design decisions, right? So everything goes at the process boundary layer, apart from the original Java implementation that I saw, which works inside the JVM, but that meant it wasn't as good for performance reasons and various things. Even, interestingly, reach.io, right? So this is JavaScript web application. They still do it at the process boundary. They have a custom browser, and they capture the whole browser from the JavaScript and replay. You don't see that. You step through the lines of JavaScript, just like in undo in Java, you step through the lines of Java, but they're capturing the entire browser execution because it's just the right place to do it. They're trying to do it at the JavaScript layer, and it just was too fuzzy. Binary rewriting, so yeah, we do that. Microsoft does that. RR doesn't, relies on the performance counters. Replay.io doesn't. They actually, because they're running in a custom browser, they actually modify the browser code. So they they do rewrite, but it's not binary jitted. It's done kind of at build time. This one didn't, the Java one, memory recording. And so, yeah, I'm not going to go through all of those. It gets a bit listy. So those are the main different sort of design decisions. Things are available. Hopefully one of those works for you in your environment, and you should definitely try it. And I don't mind as much if people try it and they say for some reason it's not for them. I can live with that, right? I'm just determined not to go to my grave without most people having tried it. Yes.
What do you mean by the binary rewriting?
Yeah. So it's this JIT approach. This JIT binary rewriting approach that do you do that or not? And yeah, basically we and Microsoft both do that. The other implementations take a different approach.
I think my impression is that it's completely invisible when you first start.
Yes.
It's like when you run the process inside QEMBA.
Yeah.
You just don't see it.
You don't see it, exactly. So when I did the thing with Doom before, that's what was happening under the hood. You just don't see it. Yeah. Yeah.
One question. How often do you record the memory? I mean, is it every milliseconds, 50 milliseconds?
You mean a snapshot thing? Yeah. So that varies. As we're running for longer, we start off snapshotting a few times every second, every sort of 100 milliseconds or so. But we quickly scale that back because we determine that this has now been running for a little while. So if it's been running for a while, chances are it's going to run for a long time yet before something interesting happens, right? So the snapshots sort of become more and more spread out over time. And except when something interesting happens, segv, breakpoint, watchpoint, whatever, we know that's an interesting point in time. That's where the user is looking right now. So we'll try and keep a snapshot close behind that. And so it's dynamic where we keep the snapshots, and we're cleaning them up all the time as it runs. We're taking them frequently, and then we clean them up, and so we kind of have a distribution. Because the snapshots are really only an optimize. They don't need the snapshots. if you were prepared, if you were sufficiently patient, you could just do every single reverse operation by going to the very beginning and playing that all the way forward.
Well, that's where I'm coming from, actually. The snapshots are where you can go to a point in time pretty much instantly. If you replay,
Yeah.
effectively you re-execute.
Yeah.
If you want to get to just before the next snapshot,
Yeah.
you've got to wait for as long as it took to record.
Yes, exactly right. Yes, you do. That's exactly, yeah.
An hour apart, you
Yeah. Yeah. Yeah, yeah. And so you can see that. So if you've got a very long running program, let's see, we have customers who run for days in some circumstances. And you can see it. So what you see is I step back, it's nice and quick. Step back again, nice and quick. And then eventually I step back over one of the snapshots, and now I have to wait for, maybe an hour for the whole thing to like repopulate its snapshots. But better than running it again, because it took 12 hours to run in the first place.
On that note, do you have the ability to go, this is my interesting window that I'm going to be exploring a lot, could you please re-snapshot bits in it?
Yeah. So you can ask it to create a snapshot. You can also set kind of boundaries. So you can temporarily set, this is my maximum, this is my minimum, and I want to kind of focus in on here. And you can also do things like, there's a print per snapshot. So you can print the value of an expression for every snapshot that we have. So people like this, because a lot of long-running programs have an internal kind of notion of time. So you kind of see, what's my internal counter, all the snapshots, and that allows you, so you can sort of do it a bit by hand if you want to kind of cheat. I want to show you, I know I've whittled on for quite a long time, but I want to show you one other thing, because I promised you some stuff about AI, right? So unfortunately, this one doesn't yet work inside VS Code. Well, no, but that's good. We see a different interface. It doesn't have to be in VS Code. So yeah, so that's my recording. So UDB is our command line thing. If you're familiar with GDB, this will look like, very familiar. This is not yet in the main line product, but I can go extend explain and it will download it. It's doing it over my phone, so hopefully it will be reasonably quick-ish. There we go. Right, so I've extended explain. So now I can say explain, please find all the times in the program execution where zombies were killed. And this is an MCP server where Claude Code is now reaching out into our recordings and like finding out things that happened. So this is an AI demo, so anything could happen, right? It usually works. Sometimes it gets there quickly, sometimes it takes a long time, sometimes it goes a different route. It's really interesting. I'm not quite sure which version this is. I think this is not the published version. This is the published version. I'm thinking the one that isn't published. What we do is we have two agents going along, and one is giving a hypothesis about what it did, and then the other one like validates that hypothesis and looks at the recording and says, I don't think that's quite right, and feeds the response back in, and it tries, and we kind of go around this loop. And it's really fun watching them talk to each other, because you know how they're kind of a bit sycophantic. So they start saying like, oh, excellent try, you're almost there, but I think there's a bit of missing on the memory. Good go, keep going, try harder. And then it goes around and it says, how about this? So it's gonna just do a bunch of stuff. This takes a variable amount of time, and it's tethering off over my phone, which probably doesn't help, but it's gonna explore the history. And the nice thing about this is it's basically a hallucination antidote. Okay, it allows that, because the trouble with, I touched on this earlier, right? LLMs are, some of the stuff they can do in terms of code generation is incredible. Claude Code is great. I hear people saying really good things about the other kind of equivalents, Cursor and all these things. But it's all really writing code. That's what they care about. That's what all these billions and billions are going into, which is like the 10% of the problem. And if you turn the LLMs to debugging code, unless it's really shallow, like all the kind of benchmarks are like 50 lines of Python with a bug on one of the lines. Not that hard, right? They can just do it. But when it's real world code, they just guess, and they just tend to tell you given the symptoms, what is the most common type of this bug? So they'll go, oh, it's an off by one error or whatever. And unless you do this, and if you point them at the recordings, now you can kind of say, well, yeah, okay, you think it's an off by one error. Let's see if we can find an off by one error in the recording. No, we can't. Try harder. And where is it getting to? So it's just going to try a bunch of stuff. We'll just have to let it. I meant to do that before I did the slides, damn it. I think you'll get there eventually. But yeah, it's not. I would say it's usually not. In my experience, this stuff is not quicker. If you're really skilled at using time travel debugging, you can probably get there maybe faster, certainly not much slower than the AI can get there. But you can get on with something else, right? You can do some other work, or you can have a beer, or you can spend time with your loved ones, or whatever it is that you want to do in the time that it saves you. So I think this is where we're going to start getting, it's going to start getting into, yeah, it's, so it's doing lasts. GDB has died with Signal 6. Signal 6 is SIG abort. Well, that didn't work. Anyway, you get the point. Yeah, yes, yeah, absolutely, yeah, but it was not recording GDB, so yeah, no, damn, never mind. Anyway, any other questions? Or we'll leave it there.
What do you do between multiple processes?
Ah, yes, that's a cool thing, yeah. So we released just over a year ago something that really annoyingly we called multi-process correlation, or MPC. It's really annoying because now everything's MCP and it's just a disaster from a marketing point of view. But multi-process correlation, so you can record, so I've got a bunch of processes, they're all communicating over sockets or shared memory or whatever. You can record a subset or all of those, and then you might, so let's say it's sockets, and you've got to receive and you want to know where did that data come from, I can step back to the corresponding send in another process to see like where that came from. So that's super useful for those difficult multi-process problems.
Yeah, after the fact of correlating those events.
Yeah, it's correlated after. So we know, because we like the way it works, because we see all of the I/O. It's kind of how it works, right? So we see all the socket data going in and out. And in the case of sockets, at least, yes, it does depend actually. It's different for sockets and shared memory. In the case of sockets, there is a certain number of bytes that have been sent. So if I've received byte 8192 on this socket, I just need to find the send of byte 8192, and that's the corresponding set. So that all happens after the event. Shared memory is a little bit more complicated. There's some actual logging that happens at record time to correlate the shared memory accesses.
Does this need any kind of setup, like building with debug symbols, or can you get it without?
Yeah, no, it does not require any of that. So I can just run like I can run ls. This is just regular ls, no debug symbols, and there you go. It just works, right? Now I don't have debug info, so there's a little bit. I can't like look at data structures and go back to certain lines, but I can still record it. The way it gets most commonly used, so it's a bit of a cheat answer. Like, yes, it does work perfectly without debug info, but you can't really use it very well. I mean, that said, actually, no, we do have people who've done that when they're really stuck and it's all they have. Maybe they're debugging some code that they don't own. So sometimes I say that time travel makes the really difficult problems easy and the impossible problems really difficult. So yeah, it all works. The more common thing is people are deploying this and for whether it's kind of IP sensitivity reasons or sort of efficiency of deployment reasons, they don't want all the debug info in the deployed version, but they still have the debug info back here. And you can take a recording of the certainly optimized build, non-debug info, you take it back here and then match it up with the debug info later. If it's an optimized build, you still get the variable optimized out horror. Although even then I would say that's less of a problem with time travel because you can usually back up a few instructions and if you're lucky, it will become live. So the variable optimized, value optimized out problem is less severe with a recording. but not solved.
Yeah,
Yeah.
makes sense.
Presumably, based on what you just said, malware researchers could use your tool
Yes.
at the point of being exploited to go backwards. Where's the weakness?
Yeah. Yeah. And in fact, yeah, that is a use case. Yeah.
You have to,
Yeah.
trace the entire operating system.
Well, if you're just looking at, no, if you're looking at the process, then no, yeah. So exactly, that is so malware researchers often do not have access to the source code, and yes, they will use this to, see what this program has been attacked, what is going on, really at the
It might be the vendor has their own malware researchers and
Yeah.
they'll have the report.
yeah.
Say, "Oh, just without our,
Could yeah. Could be. I don't know of anybody doing that, but I do know of several malware researchers who are who use this to to because they don't have the obviously you don't tend to have the almost never really have the source code for the malware, so you're trying to work out like what is it actually doing. Yeah.
The input shared that sound like a really hard problem. So
Yes.
how is that dealt?
Yeah, I'm quite proud of this one. So. It was probably the last good idea I had, actually. So the memory's changing under our feet. We need to be able to record like when has that happened, and there's basically two sensible ways you might try and do that. So we've got a JIT, right? With binary translation, we can kind of get our fingers in anywhere we want. So we can check every memory access. Is this memory reading from shared memory? And has it changed since last time I saw it? And if it has, I can store an event in my event log. In fact, you can see that Doom does quite a lot of that, actually. You can probably see it. No, I was expecting to see, no, I've got the wrong snapshot of but there's usually some event shemem fix-ups here. The problem with that approach is that it's going to make every single memory access go a bit slow. We don't want to do that. We're probably adding, probably, I don't know, 1 in 4 instructions is a memory access. And I'm talking here about adding at least probably a dozen instructions, in best case, to kind of do that analysis, probably more. But the other approach is I could use the MMU. We rely on the MMU, by the way, for the snapshots. They're copy on write snapshots, so they're nice and efficient. We use fork because it just does what we need, or clone. And so I could use the MMU. So I could say this memory is shared. So I'm going to protect that with prot none. I'm going to force a trap to happen every time I touch it, every time the program touches it. And this has the advantage that the memory that isn't shared, and nearly all memory is not shared, you're accessing a stack most of the time, and things like that, then that's not shared, that will run at full speed. But it does mean that now when I touch shared memory, that's really slow, because that's taking a fault, and it's probably, we intercept the fault and you don't see it, your program's isolated from it, but it's like a million cycles to do that, right? So the shared memory access is, if I have a very, very small number of them, that's going to be okay. But if I have any, it's going to start going really slowly if I have a lot. So what we do is both. And so we start off with all the memory that's shared, prot none. Then when something touches that, it will fault. Now we know that that instruction, at least sometimes, touches shared memory. So now we retranslate that one to do a bit slow, but not too slow thing of checking in software. And we actually got the really shared memory somewhere else, and it can do it without taking a fault. And then so the shared memory access is run a little bit slow, but not too bad, and everything else runs at full speed.
Right.
Yeah.
So a shared memory gets mapped twice.
Yeah.
The original image you protect somewhere else.
So it actually only gets mapped once, but because it's a dummy map, where it originally was is a dummy map. We call it the emulated shared map, and the actual shared memory is mapped somewhere out the way, and that's called the really shared memory. Actually, there's a third one called the third copy, because we only want to store an event if it actually changed. But yeah, I had that idea riding on my bicycle. The original idea for this I had in the shower. I've had 3 good ideas in my life. And the one before that was the idea for my PhD, which I had sat on the lavatory. Nobody has good ideas on the lavatory anymore because of these things, which is rather sad. But you can't use them in the shower and you can't use them riding a bicycle, so that's where you get good ideas. Yeah.
So like one of the troubles I have that GDB does a good job of solving is I have a library that I don't have all the source code for. I have a little bit. I can
Yeah.
point it and say this is where I've got some of the source code.
Yeah.
Let's do it.
Yeah. I mean, as you probably figured out, there is a GDB here in the mix. We haven't tried to re-implement all the GDB. GDB is good at what it does, so all the GDB commands, add symbol file, all that stuff, just work. Yeah. Awesome. All right. Well, that end the talk. Thank you, everyone.